Okay, let's go ahead and get started. So today, the whole goal is we're going to talk about hazardous areas, specifically electrical protections. We're going to talk about explosion-proof and purging pressurization today. Next week will be intrinsic safety and non-incentive. We're going to try to get through just some general guidelines and typical applications, and kind of the pros and cons that we see of each of those types, or strengths and weaknesses, as you might say. So I like to start when I train on this particular topic, which I've been doing for probably 10 years now. I like to go back to the 1986 Challenger explosion. And if you ever read up on what happened after the fact there, it was really, really interesting from an engineering perspective, exactly what occurred. And so if you remember this was the first time where they were going to have a non-astronaut that was going to be on the shuttle, Christine McAuliffe, and they had a lot of political pressure that was being put on them to make this work, because the whole country and really the whole world was kind of watching this. This was kind of a breakthrough moment overall. And if you remember, it was a really cold time of year when they were trying to do this launch. And so they had already delayed it. And, even the president was getting involved, like, hey, when are we going to do this? We need to move forward with this. We need to, make this happen. And specifically, NASA went to Morton Thiokol, who had designed portions of the shuttle, specifically the thrusters and that sort of piece, to say, hey, is it okay to launch? And they said, well, we think everything's okay, except for there's a few things, and specifically there's an O-ring that goes on these thrusters, and that O-ring at low temperatures is, we just don't have any data on what it might do. We know that the data says it's okay for below, I think it was like 52 degrees, but we don't know below that. And right now it's, 35. And so we think you should delay it. So they delayed it. Political pressures start getting pushed on them again. And now NASA goes back to them and just kind of changes the question. They say, listen, can you prove to us that it's unsafe to launch? And Morton Thiokol, all the engineers are like, we don't know, we're not really sure, we just don't have the data here, but we think it's probably not a good idea. And it got to the point where they were getting pretty heated with the whole thing. And some of the Morton Thiokol engineers even just, flipped out and said, don't do this, this is a bad idea, but we can't prove to you why not. We just, we have a feeling this is bad. And sure enough, it went up at a temperature colder than the specification had ever been looked at. And unfortunately, we all know the result of what happened. And in the after effects, what they found from a standpoint of what happened was exactly what they worried about. It was the O-ring. The O-ring got too cold, and the O-ring got brittle, and it allowed things to join up faster than they should have from a chemistry standpoint, and the explosion occurred. And so in the post-mortem of the whole event as to what happened, they ultimately brought it down to the wrong question being asked. The wrong question asked was, can you prove to me that it's unsafe? Rather, can you prove to me that it's safe? And by asking the question the wrong way, it allowed them to make some poor safety decisions. And we see a lot of safety decisions being made today that are not necessarily the right way to do things. So that's why we try to teach this and try to make sure that we're asking the right questions when we're doing design. Okay, so from a speed standpoint, I'm assuming that everyone who's on this call already knows a decent amount about hazardous locations, and this is not relatively new to you. I'm just going to go through it real quick just to highlight the fact that we're looking at a hazardous area as a place where we have an ignitable condition being able to occur, and that ignitable condition would be either, oops, sorry, hold on, I just lost something there. Sorry, my slides went down. There. All right. Basically, we see an ignitable situation where we've got flammable gas vapors or dust, and we've got sufficient energy from either electrical or thermal to cause an explosion of some sort. And so that's a hazardous area location. Essentially, if you remember from Boy Scout days, if you did that, there's 3 things in the ignition triangle: energy, air, and fuel that you have to have. And the 4 methods that we're going to talk about, 2 this week and 2 next week, essentially do something to mess with this energy triangle such that all 3 can't be present together at any one time, or if they are, to mitigate further issues. So that's the whole gist of what we're going to go through. We're talking about very, very low ignition levels if we're looking at electrical. They do tests within these test chambers where they modify the gas concentrations, they modify various voltages and currents in order to be able to see specifically what causes ignition within a gas concentration. And it's ridiculously low in some cases, especially in things like acetylene and hydrogen. The levels of electrical ignition necessary are really, really low in order to spark something. So we try to take all those things into account when we're doing our design. In North America, it does vary a little bit from Europe. Europe prefers something called the zone methods. North America prefers the division methods. Again, I'm not going to go into great detail because that's not really our focus today. We're trying to get through the pros and cons of these two electrical methods, but just be aware that there's two main divisions that the world uses, divisions and zones. Divisions typically divide things by class 1, class 2, and class 3. Class 1 is gas, class 2 is dust powder, class 3 is fibrous flanges. So we look at the nature of the hazard first, class 1, class 2, or class 3. And then secondly, we look at the division. And the division basically kind of talks about two things. One is, in a division 1, we say that's a normal operation where we assume greater than 10 hours per year of a dangerous level of gas, or whatever the nature of the thing is. Division 2 is an abnormal operation. In other words, something has to happen that would cause an abnormal situation to occur. So something out of the ordinary. And we assume between 1 to 10 hours a year of that dangerous level could occur. So we would always divide a hazardous area into a class and a division, or we'll talk about zones in a sec. So class 1 div 1, class 1 div 2. If we had like a class 1 div 2, we would say, well, that's a gas. And under abnormal operations, we'd have 10 hours or less of that gas present a year in our design criteria. We then go into groups. That's our third piece. So class 1 div 2 group, and that defines the type of thing that's there. Acetylene and hydrogen are the two that can spark most easily, and then like ethylene, propane, we'll get methane there from mining, metal dust, carbon dust, you get the idea. But then there's also temperatures that take into effect. We talked about there's electrical and there's thermal. So we can have a thermal event that can cause an explosion in certain atmospheres as well. So we always have to define the temperature in addition. There's some just quick examples of the auto ignition temperatures of various things. I always found it interesting, things like tea, 300 Celsius. So you heat tea up too much and it can actually explode. So I found that interesting. There's a quick example of what we look at when we're looking at a typical tank farm, as an example. So in this tank farm, we've got our flammable substances that are inside, so liquid fuel inside, and they're going to have some off-gassing that would occur. And as soon as that off-gassing occurs, everything where that gas is normally present, which is just at the very top of the tank and also outside the tank, that the vents are going to let some of that gas out, and even into the surrounding berms that protect it from a major liquid leak. We would all consider that a div 1 area. We consider div 2 where it's above if a leak were to have occurred, and that's that yellow area where we would expect in an abnormal condition a leakage of liquid would occur, and now the off gas is leaking into the atmosphere right there. So if like we were going to put a panel in the yellow area, we would have to make sure that that's not a general purpose panel, that that's panel designed for class 1 div 2 type area. When we get into zones, it's a little bit different. They do have a little bit of a different designation I think is useful. They have a zone 0, zone 1, and zone 2. So essentially zone 0 and zone 1 are kind of similar to our div 1. Zone 2 and div 2 are pretty much the same. The one difference that they do say is if you look at the hours, remember we had 10 hours or less and then 10 hours or more defined div 1 or div 2. In this particular case, they define zone 0 as greater than 1,000 hours where things might be present. So that is a little bit of a further designation that Europe and some of the rest of the world have. And the only thing that is allowed to go in zone 0 is intrinsic safety. We'll talk about that next week. All right, so again, here's our ignition triangle. We have 3 basic principles that we're going to follow, and those are containment, segregation, and prevention. So those are the 3 main things that we're going to talk about these 2 weeks: containment, segregation, and prevention. And all of those 4 different methods, those are the 4 most common methods, use one of those 3 in order to prevent, segregate, or contain a situation where an explosion could occur. So there's our 4 methods, and I also defined, if you look at the National Electric Code and how some of these things are defined, you'll see them sometimes as these particular acronyms EXD, EXP, EXNA, and NI, and EXI. There are lesser used methods, and we're not talking about those. I listed the 5 less common ones that we see out there, which you may have run into at time to time: hermetically sealed, dust tight, increased safety, encapsulated, or oil filled. These are very common. They're just not as common in what we get into with some of the applications that we regularly deal with, which are transmitters, VFDs, panels, things like that. Okay, so let's go through the first one here, and this is specifically the idea of containment. So if you would, I'm going to ask you if you could go over to your chat. And I ask this question because I find that often there's not enough teaching that's done on how explosion-proof works, even though explosion-proof is the top one that's used in America. So if you would, just write in the chat, if you would, just 1 or 2 of you, specifically, what does explosion-proof do whenever it effectively does what it does for an electrical protection method? How does it work? Can anyone give me some guesses as to what you think it does? And I'll wait for you as you write those in your chat. While you're hopefully writing, we have an example here of a panel that is a common panel that you might see that is an example of explosion-proof. It's got a lot of a lot of metal, a lot of bolts, a lot of that sort of stuff. Right? All right, so we got a couple of people that have written in. Thank you. All right, so we have keeps the panel and the motor from propagating an explosion. There's an explosion in the panel box that contains it and keeps it from spreading to the rest of the area. Containment, small leakage path. Okay. Prevents heat from escaping. Yes. So we asked this question only because it's surprisingly confusing out there as to how it actually works, and because people don't really understand the rule, they take a lot of methods that they cheat on because they don't fully understand it. So we like to ask those questions so that we can make sure that people really get it. So we're going to start with specifically, what does the NEC say? And the NEC defines it with 2 rules that are really important for you to get. And I want you to read through these because there are 2 factors to these that most people will miss out on. Number 1, must be able to contain that explosion, and there's a key word here that I want you to see that's twice here. Must be able to contain that explosion enough, or prevent an internal explosion enough to prevent a much larger explosion that's going to be external to the box. So the key word here is enough for both of those. And there's a second rule, and that basically says you got to keep the temperature of this whole thing, both inside and outside. You got to keep this temperature down below the level where it could cause an explosion either inside or outside of the box. So the key piece here is enough, and that enough is the one that a lot of people will miss. And that's what we wanted to talk specifically through today and look at some of the things that you guys defined. So here is just a real easy, simple example of an explosion-proof thing that you'll see. So I showed that box that was right there. There's a sample box that we're all familiar with. We're all used to seeing the thick metal that's super heavy. This box probably weighs 50 pounds at least, and it's got all the the bolts. Probably 10 bolts per side, and we're used to that overall. But here's what actually happens with these things, if you're unaware of it. So when the panel maker or the transmitter maker or the motor maker, whoever, when they design these things, they make them with a specific gap. And that gap is specifically designed so that they assume that an explosion could occur inside that panel. And when the explosion occurs inside the panel, they need to make sure that, number 1, it doesn't become a bomb. They don't want this thing exploding and shooting metal shards everywhere. But they also don't want a situation where that explosion occurs and now it comes to the outside and causes a secondary explosion. And so they have a flame path length where the idea is if that explosion occurs inside, they make sure that as it comes to the outside, it eventually gets to the outside with too little energy to cause a secondary explosion. And this flame path is really, really important to the design of how any of the panels or the transmitters or that sort of thing works. And so if we were to look at some of the places where this method is used overall, we tend to look at it at places where it's going to be higher powered type applications, applications where we need to put more power in there than those. Remember I showed you earlier on the electrical ignition levels are very, very low. So, things where we need like 120 volt power, or we need a lot of amperage, those sorts of things. That's the place where XP is really strong and is used. And it's used because, for the most part, we can put heavy metal around something and mitigate everything getting to the outside and causing a secondary explosion. But here's the ways that it wouldn't allow that to occur. And so I'll share some of the examples. When I taught this the first time, probably 15 years ago, I had a company that was a gas company, and they were present there. And as I'm saying these things, I see the guy, he was a manager, and I see him just putting his head in his hands, just like, oh my goodness. And I said, hey, you're putting your head in your hands. Either you're feeling sick because my teaching's really bad, or else I just said something that made you depressed. And he goes, I'll tell you right now, something you just said, I just realized we do all the time, and I had no idea the danger it was causing. So two things here. Number one, a compromised flange could be a problem where that flame path, if you give it too much of a flame path, you could let it get out with enough energy to cause a secondary explosion. So if you've got all kinds of scratches, as the guys take off the front of the panel, they take that off, and they're kind of scraping the metal against each other as they do that. They're creating little extra paths that could cause a problem. But the bigger one is not that. The bigger one is this one. And this is what caused the guy to hold his head in his hand, the forgotten bolts. And almost every single time that I've taught this, people, I see them nodding their heads, because what do a lot of the maintenance guys like to do? They hate having to take off those perfectly torqued, 25, 50 bolts that are on this thing. It's just a royal pain in their butt. And so when an inspector comes around to audit and look at things, they want to see all those bolts in place. So what a lot of the guys have done is they'll either get lazy and they'll just put the 4 bolts in the corners on and leave all the other bolts up, not there at all, which now creates plenty of extra place for gas to get in to cause an explosion, and leaves even more for once the explosion occurs to get out and cause a secondary explosion. Or they'll do something even worse. In order to fool an inspector, they'll put just the 4 corner ones on, and then they'll use a sawzall and cut off all the bolts on the other ones, but glue them in place. And if you do that, you have effectively created every single one of those things to be a bullet if an explosion occurs inside. You've now created a bunch of bullets that shoot out at high speeds to anyone that's standing in front of them and can cause some significant damage. So this is the biggest one that we see overall. Here's another one that we see that's a big deal. So if you imagine that panel, let's say that we do everything right. We put all our bolts on, we don't have our flange is not compromised, or if the transmitter, where I have that transmitter perfectly closed, I haven't put any kind of sealant on it or anything because I need that flame path to allow it to get out and not create a bomb. I put my transmitter in place, but the electrical contractor that I hired to install everything forgets to do the seals. So whenever you install any sort of a transmitter, or whenever you install any sort of a unit that is a explosion-proof panel or what have you, you have these seal-offs where you put everything in, you wire everything up. Usually you start it up knowing that it's a safe condition. You use a little sniffer of some sort, make sure that the area is safe so you can start it up. And then once everything's safe, you're then supposed to come back and put the sealant in those seal-offs to make sure that if gas were to leak in to your panel, that it wouldn't have a path to then leak back somewhere else. And sure enough, I did this training, I don't know, maybe it was 10 years ago, at a major gas pipeline company. And they, again, kind of sheepishly looked and they said, yeah, we had that exact situation just happen, and it blew up our control room. We put panels in, and our electrical contractor forgot to put the seal-offs in, forgot to put the sealant in the seal-offs, and the gas got in our panel, leaked 100 feet back through the conduit, and got into our control room, blew it up. So another major weakness. These are the two big weaknesses we see, forgotten bolts and forgotten conduit seals. Lesser weaknesses are obviously the heavy and expensive metal. These things can really weigh a ton and can get ridiculously expensive, especially now with metal being expensive. So generally, you don't want your panels to be too big when you're doing this, because it's just, the weight is ridiculous. You can't attach it to a wall. You have to make it freestanding. The other thing that people do forget, I rarely see it being an issue, but in certain applications, if you forget about the temperature specs, and the inside of that panel builds up some significant temperature from the electronics that you have inside, you've got an issue then where the temperature specs have been forgotten, and now you could have a thermal event as well. So those are your weaknesses of XP. All right, we'll save any questions or comments on that one until the end, but I'll just go through some of the typical XP applications. High power motors, process transmitters is a big one, like industrial process transmitters for Div 1 areas. Panels with higher power unclassified products that are inside of it, very common. Lights, horn, safety equipment, very common that you see those as explosion proof, and a few pumps out there. So those are probably your big five where you see XP being used as a pretty common solution overall. And it is the most commonly used in America. Okay, again, save questions to the end if you have them. Let's jump to purging and pressurization. We'll finish off our final about 5 minutes with this. So whereas the first one was more of a containment that then prevents a secondary explosion, and so whoever said, I think it was Chris, said keeps the panel motor from propagating the explosion, and that's correct. Explosion could occur. We don't want it to propagate into a secondary one. All right, so now tell me, what is the purpose of purging and pressurization? If you guys could also answer that. What is the rule? How does this work? How does purging and pressurization work? What is the concept? So if you guys would chat through that for us as well. And then I'll also show you here on the right, we have a pretty common example of what a panel looks like. All right, so we have first answer, removes oxygen within our gas. Any other ones that people have on there? Any other comments? We'll give it a couple seconds. Prevents gases from entering the enclosure. Second answer, keeps positive pressure to keep gases out. Yep. Okay, well, thank you for some of those answers. So let's go through some of these and just make sure that we explain to them and how this is going to work exactly. All right, so here's the NEC rule, defined by the National Fire Protection. So that's the NFPA. It's a group of various rule sets that have been put together. Specifically, Rule 496. We're going to reduce, limit, or eliminate hazardous gases or dusts by using positive pressure ventilation with clean air or noble gas. So oxygen could be present on the inside of this. It absolutely could. What we're trying to prevent is the gases that are the explosive gases from getting in. So even if oxygen is there, we are trying to prevent the gases from getting in. So we're keeping that positive pressure to keep those gases out. So good job to everyone that got that one pretty closely right. There's three basic terms that people use with this: X purge, Y purge, Z purge. I rarely see anyone use the Y, but X and Z are pretty common. And it's really defined by the division that you have the panel, and these are almost exclusively panels or analyzers. Those are the two main places. Sometimes motors, but panels and analyzers are the two big places. So I see it. So if you're putting a panel or an analyzer in a Div 1 area, and the stuff inside that you're trying to protect is general purpose, which most of the time it is, you're going to use an X purge. An X purge has to follow certain rules in order to be able to make sure that we keep all the gases from getting in there. If you have a Div 2 area, it's a little less strict, and we use a Z purge. A few less, clearing out the internals enough first that you can turn everything on and make it work. All right, so here's your gist of how it works. Two major people that make these things are Bevco and Expo. They both work basically the same. The idea is that they pressurize air or inert gas, like a nitrogen or argon, but nitrogen is probably far more common. A pressurized air is fed into a sealed enclosure, and it's not really truly sealed. It has to breathe a little bit, but it's pretty sealed. So it's enough that it can hold a pressure if you're pressurizing. We try to make sure that it's kept to at least 0.1 inches of water, so enough that The inside has enough pressure as compared to the outside that it'll always be a flow outward, not a flow inward. And then we've done at least enough volume exchanges of protective gas before power is permitted into the panel. So for a Z purge, they want you to do 4 total volume exchanges, and that's just a calculation that you have to do based upon volume and flow. You calculate the amount of time that'll take. With an X purge, we generally like to tell people that they should do 10 total volume exchanges just to be extra safe. So those are kind of the rules as to how that works. This is what it looks like. So a lot like, this is a panel that you would see with a purge, a lot like the bolts that you see on an XP type application. Here we're going to have latches. So we're going to have a seal on this door. We're going to have latches all over this thing. And we're going to make sure any conduits are sealed and all that sort of stuff. And the idea is we're then going to pump air or inert gas into this thing enough that we can't put too much in or we'll bow it outward. We put in just enough to achieve the pressure that we need and then kind of dial it back. So it always has a positive pressure. But generally with these sorts of panels, they have to have a stronger seal. NEMA 4X almost is demanded. We have to have stronger metal so things don't bow out. Any kind of electron. In the old days, you used to have some of the displays would actually bow outward and even pop. So the newer ones are able to handle that for the most part. If we have any kind of buttons or anything like that, those all have to be able to handle that pressure as well that's on the inside. So some of its strengths for panels, high-powered motors, where it would be really impractical to have a heavy metal cabinet. You need to be able to see things and touch things, buttons and that sort of stuff. And it's just not practical with explosion proof and all the bolts and all that craziness. That's where purge is wonderful. It's not too difficult to understand. Everyone for the most part gets how it's how it's used. It's great for dust and also for applications where you might have bad gases that would wreak havoc on things like ammonia or chlorine. Pressurization will often be used with those areas as well. However, it can be difficult to seal. So I've been able to help some of the panel manufacturers whenever they're doing their tests to get these things going, and they'll use things like bubble gum and silly putty and all kinds of silly stuff to try to find where their leaks are coming from to try to get this thing to be able to achieve that 0.1 level that they need to of pressure. Sometimes they'll forget to do the conduits, and now it's just leaking out the conduits, and so it can be challenging if you don't use a panel with a good enough seal. You often have to even put a secondary seal on the doors or put extra latches just to make sure that it's not creating enough of an area that things are leaking out. You got to have a little bit more engineering know-how than explosion proof, just because you have to make sure that you're doing calculations and all that sort of thing. Continual source of protective gas needed. You've got to have an air compressor, or if you really want to be extra careful, you use like a nitrogen feed. But you can't just use a simple little tiny compressor. You have to use a compressor that can achieve at least 60 psi continuously forever in order to be able to make this happen. And if you ever want to do live work inside that panel, you've got to shut it down and get a gas sniffer to be able to put any of the power on inside this thing when the purge is not there. Okay. So that's kind of our conclusions here of the 2 XP and purging. We're going to do intrinsic safety and non-incentive next week. But with any of this week and next, we're going to try to really remember to teach you, just with the Space Shuttle Challenger thing, ask the right question. A lot of times we'll see that people are trying to cheat, or people are trying to cut corners or things like that. And we have explosions happen all the time in America because people don't take into account they're asking the right question. They cheat, they cut corners, they create bombs with their panels and let the bullets shoot out because they use a sawzall on their bolts. Like, it happens all the time. And so just make sure that you do that. If you're the engineer designing this system, remember, you're going to have an electrical contractor putting that in who may not have a lot of expertise with this. So make sure that you triple check the design and triple check the implementation afterwards. Don't miss some of the seal offs. Make sure the bolts are torqued correctly if you have an explosion-proof panel. Make sure you have enough pressure with the purge and everyone understands how it works.